Hello, everyone. This is Team Pretty Good BGP. We're presenting on Poisonous Defense, Circumventing BGP Level Censorship. I'm Curtis Leba.
I'm Ryan Schmidt.
And I'm Austin Derbick. The motivation behind our project is to look at how we can prevent censorship on the open internet from spying or censoring entities. Essentially, we can do this based on existing research that was conducted for mitigating distributed denial of service attacks. In real case scenarios where censorship is a problem, we can look at either China or Myanmar, where government agencies are spying on their people. This leads to the need for a way to route around those censoring entities and allow uncensored access to the internet. The group description here, we broke down various tasks for each of us individuals, where Ryan Schmidt handles the provisioning of network resources, myself, Austin, creating the test network, Curtis Leba running the services on the test network, followed by creating a path poisoning utility, which is used for carrying out the attacks as a form of defense, and then testing that path poisoning utility to ensure that it works successfully, and then enhancing that path poisoning utility. The technical details of this project include a VMware ESXi server, which on top of that, we have 12 different virtual machines. These are all configured using Ansible as the configuration management server, to where we deploy the various bits of software. We use FR routing as a means of handling the BGP implementation, with Nginx web servers on each of the leaf nodes to test connectivity between our end users. Finally, we use Python as a means of running the poisoning attack and collecting experiment results.
And what you see here is a diagram of our test network. The blue nodes represent AS's autonomous systems. These run the BGP protocol and can route packets between them. The lines indicate which autonomous systems are connected to each other. The red nodes are also autonomous systems, but they are what we designated as censoring entities. We are attempting to poison those nodes out of the path so that we avoid them. And the yellow nodes are our leaf nodes that are running the Nginx web server and are being used for end-to-end testing. And so here you can see that we have Ansible as a separate controller node that can push deployment information out to all of the autonomous system and leaf nodes. This greatly simplified our networking setup and allowed it to be resilient against any misconfiguration, and greatly enhanced our ability to run repeated tests and get results. So when we conducted the testing, we tried 5 different experiments. The first is we did not do any poisoning, and we can see that between all 3 of the yellow nodes, there are 8 total routes. The top left to each of the bottom ones, the bottom each of the other ones, and so on and so forth. And by default, 4 of these 8 routes were intercepted by the AS 64518, that is the top left censoring node, and 4 of them were intercepted by AS 64513, the bottom right one. Then the first experiment, we poisoned off the top left node, that is the red slash that you can see in the diagram. And we see that we successfully avoided routing some of our routes through that, but they went through the next AS 19 instead. We continued doing poisoning, poisoning 2 nodes and then all 3 off the network. And you can see on the slide how that impacted the routing. Note that because the bottom right yellow node is behind the censoring node 13, it was impossible for it to reach anywhere else without going through a censorship node. So the network topology can prevent circumvention.
So this project has several novel aspects. The most important focus of our project was taking a BGP poisoning strategy, which was generally used as either an attack or a defense against DDoS attacks, and turning it on its head and using it as a way to mitigate the effects of censorship. During this project, we faced several challenges, such as figuring out how to provision a reasonable test network and efficient ways to collect test results. And we identified the limitation of this project in that path poisoning can't get around the fact that isolated nodes can't find their way out of censored networks. Now, the project has a lot of benefits potentially to BGP in the future. For instance, this provides a novel technique for evading censorship and surveillance. So by the end of our work in this project, we've been able to provision a simulation network. And we created this test network in a way that allowed us to test a variety of situations and experiment with the impact of topology on our method. We were able to run our test services on the network, including the path poisoning utility, which took advantage of built-in BGP commands. And we were able to test and enhance path poisoning in the sense that we were applied it to a new domain of censorship. To conclude, we were able to successfully alter routes on a BGP network with BGP path poisoning, and we were able to further use that result to mitigate the effects of censoring ASs on a BGP network. And in the future, we'd be interested in the ideas of distributed path poisoning using a variety of ASs in the path poisoning, and it'd be interesting to look into the impacts that this technique has on the internet freedom of users, and also what sort of countermeasures censoring agents can apply to the network.
To review our network topology, we have the diagram displayed on screen. You'll see in the bottom left-hand corner this yellow node. This is one of our leaf nodes. It's going to be the user or an actor trying to communicate to a web server in the top left-hand corner of the screen, that other yellow node. Now, in BGP routing, or otherwise known as Border Gateway Protocol, we essentially try and find the best route to that node. So the bottom left node is going to follow the given route traced by the mouse on the screen. And as you'll see, it goes directly through this red node. That red node is a censoring node, and that's a problem. But before we give the solution, we're going to display to confirm that we can retrieve the packets censoring information from these two nodes communicating with another.
Right, so what you see here is a handful of terminals. The top left terminal is our, represents that node at that yellow node at the bottom of the screen, the one that we're trying to query the web server from. At the top right is the censoring node that we drew our path through. If we dump packets on it, we'll eventually see things flowing through it. This bottom right is another censoring node from our topology. We'll switch back to it real quick and show you. So the top top right was this one. Bottom right is this AS64519. And we are trying to go from this bottom yellow node to the top yellow node. So we'll see that.
And using a curl command, we're able to query the web server.
Yep. And we can see that indeed packets did go through our censoring node, number 18.
Next, we will show how path poisoning can change the route in such a way that it circumvents that censoring node, and packets will no longer be able to be captured from node 18.
Right. So in the top right terminal, you'll see this is the list of BGP paths. And importantly, these are the paths coming from node 18, the censoring node. And you'll see that has a direct path to AS21 64521, which has a path to the end host, which has the web server. And so this is how the network is set up before the poisoning. And so when the poisoning actually happens, what's going on under the hood is that we're taking advantage of BGP's AS path prepinned features and also loop detection, which is generally designed to be a good thing, but we're using it to convince AS18 to drop one of the paths.
The bottom left-hand corner, you'll see that Ryan is about to execute the poison command, which is our way of performing BGP path poisoning to that censoring node.
Right, and this is done by constructing and engineering a fraudulent path that gets announced through the network and then convinces other ASs to drop paths to prevent loops.
Yep, and you can see that the command succeeded and the poisoning should have been successful. We can verify that by taking a look at what our routing tables now look like.
Right, and so now if you look at the third to last route here to 10.0.2.1.0, that path no longer goes through AS directly to the AS 64521, and that's because this censoring AS has been poisoned and convinced that the original route would lead to a loop, and so it dropped that route and has adopted a new one.
Yep. And to confirm this, we will now repeat that original query to the web server from the bottom left-hand node to the top right to the top left node with a packet listener on that censoring node. And if any packets are displayed, then we were unsuccessful. If no packets are displayed, then we'll know that the route has successfully changed, circumventing this censoring node.
Right, so we'll do that, and we can see that we no longer have packets on node 18, but we do now on 19. If we take a look at what the topology diagram looks like, what happened is we knocked out this link here so that 18 cannot directly talk to 21, and our packets are now going through this path, which is why we were able to see on 19 the packets happening. Next, what we're going to do is knock out this path as well to show that we can completely avoid all censoring nodes on the way from our source to our destination. So here's the command to poison that link that we just showed you. This will take a little bit of time to run, and now that we'll have both of those links out of the picture, we will see that we no longer have any traffic here or here on the way between the two nodes. And just to
clear your screen
one more time. Tried it 3 different times and no packets are flowing through either of those two censoring nodes. So the poisoning is successful.